My name is Mike Ribeck. I'm a grad student in Richmond Lab, and I'm going to be talking to you about an analysis of variance in fitness over 50,000 generations in a long-term evolution experiment. So, like other people in the session, I'm working in experimental evolution. The particular system I'm working on is the long-term evolution experiment in Richmond's lab. This is a long-term experiment that's been ongoing since February of 1988. We have 12 populations of initially isogenic E. coli. Every day, each one of them is transferred by diluting it 100-fold into a fresh, sterile media of minimal glucose. That means they go through 100-fold growth every day, so it's about 6 2/3 generations. We've recently passed 60,000 generations. And one of the great things about working with bacteria is that we can freeze these things at -80, and they are viable indefinitely. So therefore, I can compete populations from the present against their ancestors from 25 years ago without having to rely on data other people collected. So back in the fall, we published a paper looking at the mean fitness trajectory as this moves through time. We compared a couple of different statistical models. The blue one here is the one that's a much better fit. This is a power law dynamic. This shows that adaptation is going to be predicted to continue indefinitely. It doesn't actually have an upper limit. Whereas the red line here is a hyperbolic fit that has an upper limit to what fitness would reach. This is showing also the fact that the power law does a good job of predicting future fitness. These are fits fit through the first 20,000 generations, which are the dots in dark. The circular open dots are fitness that I measured for later time points. You can see that the power law predicts what those are going to go through. The asymptotic model does not. At this point, however, that was just a statistical model. Within this paper, Noah Ribeck, a postdoc in Rich's lab and my collaborator on this work, ended up deriving a dynamical model trying to figure out how fitness should change using more population genetics parameters such as population size, effective mutation rate, distribution of beneficial fitness effects, and what the strength of diminishing returns after stasis is going to be. So now we're interested in looking to see how does the among population variance change over time, and whether our model can actually predict these changes in variance. So from these populations, we know that 6 of them maintain the ancestral mutation rate. So I'm just going to be talking about those 6 that are not hypermutators. These are the ones that we've modeled so far. So using Noah's dynamical simulations, we modeled a whole bunch of populations. If I take random sets of 6 of them and look at what the variance among populations in fitness is going to be over time, you can see that this is actually ridiculously small. That's showing both the mean and the 95% bootstrap confidence intervals around it. Variance is really small if you hold the diminishing returns at the stasis parameter constant. On the other hand, if you allow that diminishing returns at the stasis parameter to change every time a new mutant has arisen and swept the population, you can end up with this increase in variance over time. This is just one way of allowing this to increase. We haven't gone through and finished modeling the different levels of potential increase or the different ways in which this parameter can change. All we're talking about here is just that this is a variable one as opposed to the constant one. Now, from the empirical data, in addition to having all of the fitness values, we can then go through and calculate what is our among population variance in fitness. So this is the data from the paper back in the fall. You can see that it is a little noisier. This is empirical data as opposed to simulation data, so there's going to be measurement error, as well as the fact that we have these different populations. I was worried at first about the fact that each one of these is based on 2 replicated measurements of fitness per population per time point. The fact that we're measuring variance, which is a higher moment statistic, means that a small degree of replication results in potentially very large error. So I went through and took a smaller number of these points and increased the replication level on those. So those are 5-fold replication on those time points. You can see that you're still getting fairly consistent results across the 2 of them. If we then create a weighted model where we combine these 2 data sets and we weight them based upon the number of replicates used in each one of them, we can say that this is what we get as our among population variance just as a grand mean. This is not looking at it changing dynamically over time. I can tell you that when we fit a linear regression to this, we don't actually get a significant slope value. We get a slope that looks positive, but it's not statistically meaningful. We're looking at various different ways of modeling how that might change over time. So looking at just the empirical data, you can see that for just a grand mean, that is clearly going to be higher than 0. So we do have some degree of among-population variance over time. This is also going to be larger than what we get if we assume that the strength of diminishing returns at stasis is constant over time. So this was what it was if it was constant. Here, if I add them together, and here, if I zoom in so you can actually see the difference on those axes. The higher points here are the green lines, those are the empirical data. The ones in black at the bottom are the simulation data. You do have some degree of increased variance early on in the simulations. This is driven largely by individual populations receiving their first beneficial mutation at slightly different time points, and your first mutation is going to drive some degree of variance among the populations. On the other hand, if we compare our empirical data to our dynamic simulations where the among population variance in fitness is variable over time, we can find that this is actually well within what we expect. Now, we appear to have overestimated on this particular simulation how much variance we should allow among our populations, but it's still within the 95% confidence intervals. These are not distinguishable from each other. So our data tends to be much more consistent with a varying degree of epistasis over time, rather than forcing the diminishing returns parameter to be constant over time. Now, as I said, this is empirical data, and empirical data tends to be inherently noisier. So with the simulations, we can get what the true variance is among the populations. With the empirical data, we are estimating what that's going to be, and there's going to be differences between the true variance and our estimated variance due to our sampling effects and just due to measurement error. However, while you can tell, obviously, some of these are going to be measurements of error. Clearly, we can't actually have negative variance among populations. It's an artifact of the way that this measurement is done. I can go into detail for that later if anyone's actually interested, but I don't plan on boring you with those details right now. You can still see, however, the vast majority of these points are going to be above the 0 line, which means that we have more things in the range of plausible values than things in the range of implausible values. We can also look to see the sheer fact that each one of those points is independently measured means that we can get information about how likely it is that our data is showing actual variance among populations. So if we were to look at a cumulative relative frequency, this is what the null distribution would be. This is from a uniform distribution, basically saying things like, you would expect that 70% of your p-values chosen randomly would be a p-value of 0.7 or less. If we then compare what our actual p-values are from each of those individual ANOVAs, we can see that there's a drastic over-representation of small values here, which means that we do actually have some degree of significance across our data set as a whole. We've done stats on it to prove that those are actually real, so very highly significant. This is from the pooled data. I can tell you that this is also true individually from either the data set we published back in the fall or my new data that I went through separately. So our overall results tend to be that our variance is small but positive, and that this is not consistent with a fixed strength of diminishing returns epistasis. But this is much more likely to be explained by diminishing returns epistasis varying over time. Now this is just showing some of our preliminary simulation work with this, as well as comparisons to the empirical data. Our future directions involve the fact that we're looking at more extensive simulations, so we can try changing the degree to which the diminishing returns epistasis parameter is allowed to change over time, and the way in which this is derived. NOAA has developed several different methods for trying that. Right now, the simulations are running a little slower than we'd like to deal with the fact that we also know that some of our populations have radically increased their mutation rate. And so if we want to be able to compare populations that aren't simply the ones that maintain the ancestral mutation rate, we need to be able to simulate changes in mutation rate over time. That's in process. We also have empirical data on pairs of evolved populations. So a different way of addressing how much variance we have in populations over time is to look not just at each individual time point, all of the populations competing against the ancestor, but to take two different populations from the same generation and compete them against each other. So I have a bunch of independent pairs of populations. Here's an example of one of them. The open circles are each individual replicate. The dark circles are the means for that particular generation. And the purple line here is a local smoothing function that allows you to do an estimation for what the overall fitness compared between the lines is. This one is one of the particular patterns we happen to show, where one of the populations gets a little more fit than the other one for the first, say, 15,000 generations, and then the one that was losing catches up and gets back up to the previous fitness. We are going to be comparing our simulation results to these empirical data for each of our different pairs to see whether the patterns we see in our empirical data are outside of what we would expect from simulations, and whether this does in fact give additional support for the idea that we need to allow the diminishing returns of a stasis parameter to change over time. With that, I'd like to acknowledge members of the Lenski lab, in particular Noah, who is the co-author on this work, Jeff Jayla, who is our lab manager and keeps everything running and keeps glassware, which is really helpful, and David Bryson is a former student in computer science who I've been collaborating with, running these same sorts of analyses on fitness trajectories in a very different system, a computational system, to look to see whether this is a generalized phenomenon or if it's specific to our system. And other than that, I have some time for some questions.
Your time trace of estimates and variance again show an decrease in variance, which is in itself is consistent with increasing variance.
Well, so we do have some possibility that we have an increase in variance here. The problem is trying to figure out what we can say statistically about whether there is an increase in variance here. So if we do this as a simple linear regression, we don't have significance on that. If I tried fitting a few other functional forms to this, so I've compared, say, a hyperbolic model or a power law to this, they give substantially better fits than the linear regression does, but the R-squared values are still terrible. They're not very good predictors.
I mean, the variance about the line, that variance is getting larger as you go along, which would be consistent with an increase in variance, which would increase the variance of the variance.
Yes, that's possible, but I hesitate to draw conclusions on that just because that gets to an even higher moment statistic, and I'm not sure I have sufficient replication to say anything with certainty about it. Yes, Christina.
Talk a little bit about how the epistasis parameter changes. So is it changing in a monotonic way, or does it go up?
Okay, so the simulations I happen to show here are ones based on the idea of the diminishing returns epistasis parameter is a parameter called G in our model. When it's held constant, that G is the same G value at every point along the way. When that is allowed to change, every time a new mutation has updated through, a new G parameter is chosen in these ones from this is from the compressed distribution. So the upper half of that is a normal distribution. The lower half of that distribution is skewed such that it essentially mirrors the upper one without the possibility of going into the negative realm. The overall variance on that, I'm sorry? It can go up and it can go back down, and each one of those is individually uncorrelated to the previous one, although the distribution of potential fitness effects does update iteratively, so there's some history of that through time. Yes?
Could I don't know much about your model, but could varying other parameters in it give you a similar shape to the data with increasing variance like that?
So the fundamental model here basically has 4 biological parameters to it. So population size, beneficial mutation rate, distribution of beneficial fitness effects, and the diminishing returns on the stasis. We know from our actual empirical data that in these particular populations that I'm basing the empirical data on, the mutation rate has remained constant. Population sizes only change very relatively smallly. So there is the possibility of this feeding in either from changing in the strength of diminishing returns on the stasis or in the distribution of beneficial fitness effects. That distribution of beneficial effects in this model also feeds into the diminishing returns of stasis, so they're not completely independent parameters in the model. Yes?
How big is the within population variance in fitness relative to what's going on in the among population variance?
That depends on these individual time points. So the way the among population variance here is calculated is that each one of those individual generations, we perform an ANOVA, we subtract the mean square of the error from the mean square within population, and and divide by the number of replicates, and that gives us the between population. So in cases where it's a negative number, those are cases where the within population variance tended to be smaller than the error. And I'm out of time, so thank you all for